Good.
Good. What about you?
Good. Sorry I'm a few minutes late.
It's fine.
Sometimes it's tough when you have back-to-back appointments to get out of one and get into the other.
Yeah.
So, what do we got today?
Just jump in it. I have a test tomorrow, so I'm just going to kind of go over some of the stuff that we've done.
Okay. You want to verbalize it?
Yeah.
Okay.
So the first one is, how do you condense this expression? That's 3 log x minus log base 2.
Okay. First of all, that's not log base 2. That is
sorry.
Common log
Log 2.
Of 2, yeah. In other words, the base is generally the number that goes here. If it's not specified, it's 10. Okay? So this is log base 10. So the fact that I'm subtracting 2 logs means, well, what's the first step?
I know that you have to do division, but I don't really...
Well, the first step really, let's review the 3 log rules. In other words, when you are multiplying inside the argument, you're going to add. When you are dividing inside the argument, you're going to subtract. And the key one is when you are exponentiating, you're going to multiply. So if I do the reverse on that, from rule number 3, what do I have?
X to the third?
Yeah. So this becomes this. Now I can apply the second rule. So what does this whole expression become?
Log base, or log, and then x to the third divided by 2.
Exactly. Okay? So these 3 rules govern all of these expansions and compressions. What's the next one?
Alright. The next one is about how to kind of graph, but just get the point. So it's y equals log base 3, and then x minus 4 plus 1.
Okay, to graph these, what they want you to do is figure out the horizontal and vertical shifts, stretches, and reflections. In other words, in order to figure out how to graph that, I need to know how to graph the elementary function. What's the elementary function?
Log base 3.
Of x. Log functions look like this in general. And they look like this whether it's log base 3 or log base 7 or natural log or log base 10. They all go through this same point, which is 1, 0. Why? Because the log of 1 is always 0. In other words, the log base 17 of 1 equals 0. The log base 1,000,000 of 1 equals 0. The log of any number is, the log of 1 is always 0 no matter what the base is. So the difference between that, the elementary function, and this, you got 2 things going on. You got that, and you got that. Let's talk about the easier one. What's the plus 1 do?
I thought that's where I put the asymptote, but
Well,
Not too sure.
no, actually not. This is a vertical shift because it comes after the function. Notice that it's not part of the natural log or the log function. It comes at the end. So if I'm going to take my curve and move it up 1 is what I'm going to do. If that's all I was doing. In other words, if I was plotting y equal log base 3 of x plus this 1, I would just move the whole thing up 1. And this point would be right there, and it would look like that. Okay?
All right.
Well, I'm doing 2 things to it. I'm going to move it up 1 to there, but this minus 4 inside the argument does what?
It shifts it to the right 4.
Correct. Now this is where you want to move your asymptote, because right now I have an asymptote of x equals 0 on my elementary function. Well, if I'm going to shift 4 to the right, I'm going to move my vertical asymptote 4 to the right. So my vertical asymptote goes to there. Now this function is going to be asymptotic with this vertical line, and I know that the key point that is in the elementary function is going to shift 4 to the right and 1 up. So the point 5, 1 is in my function. We'll call that 5, 1, even though it doesn't look like it. Doesn't matter how I graph it. That point is in our function.
Yeah.
So as long as I draw a curve that's asymptotic to that and goes through 5, 1, let's do it like that. That looks a lot nicer. This is my curve. Whoops. Notice that this curve has been shifted 4 to the right and up 1. And that's the key. And the only real point we knew on the elementary function was 1, 0. So we merely have to take that point and shift it 4 to the right and up 1. So we know that 5, 1 is on our new curve. That's approximately there.
All right.
Okay. What's the next?
All right. Okay. The next one is it's just condensing this, and it's log x plus 1/3 log y.
Okay, we want to handle the coefficients first. So what can I do with this 1/3?
Make it log y to the 1/3.
Now becomes a simple process of combining both of those. What is it?
So it'll be log x times y to the 1/3.
Exactly. Okay?
Sweet. The next is expanding, and it's natural log 4 of x to the 5th, and then y.
Like that?
Yep.
Okay?
I just don't really understand how to expand.
Okay. Well, we got 3 things being multiplied.
Mm-hmm.
So let's first of all separate those into addition. So that's the log of 4 plus the natural log of x to the fifth plus the natural log of y. That's step one. And then this 5 we can put in front. In other words, expanding is the opposite of compressing. Whatever we do in compressing, we do the opposite when we expand. There's your expansion.
Okay. That's simple.
If we started with this, and they said compress, the first thing we would do is take that 5 and put it right there.
Yeah.
Then we would multiply 4 times x to the fifth times y, which gives us that. So you definitely want to be able to go both ways, expanding and compressing.
All right. I think I have a grasp on that.
The only ones that might give you problem would be something like this. Do this one for me.
Would it just be log square root x minus log 2?
Minus log of z. That's a z. But then what does that actually mean?
I don't know.
It means the log to the 1/2. When you take the square root of something, it's the same as taking it to the exponent of 1/2. And then you can take that and put it in front. So it actually becomes that. That is equal to that. So it becomes 1/2 the log of x minus the log of z.
Yeah. All right.
Okay? And that is probably the only thing that would give you problems is radical signs, if you're not used to them.
I think I got on that now.
Okay. Do you have any log equations? We should try to solve some log equations because there's some unique aspects of that you need to be aware of.
Like what?
Oh, something like log of x plus log of x minus 1 equals 2. That would be a log equation. How would I solve this?
First you would condense them, so it would be log of x squared minus 2x.
Minus 1x
Equals
2.
And then
Now,
that would be 10 to the second equals x squared minus x.
and then you have a quadratic.
Yeah.
You factor it just like you would any quadratic, solve it. The difference is that you're going to have two solutions for that, right?
Yep.
One's positive, one's negative. The negative one doesn't work because it violates the domain of that right there.
Yeah.
So when you use a quadratic to solve a logarithmic equation, you almost always have one extraneous solution. You usually come up with two solutions, but only one of them is valid. And the thing you have to check for is to make sure you never are taking the log of a negative number or 0. And you always have to go to the original equation to check, not this second one. This second one may look like a clone of the first one, but it really is not. In other words, it's possible that the domain might pass there, but it wouldn't pass up here. That makes a difference. In other words, let's take a simplified version. Let me make it log x plus log x equals 1. Now that gives me log of x squared equals 1, which gives me 10 equals x squared, which means x equal plus or minus root 10. Well, the minus solution does not pass the domain of that initial equation. Notice that it does pass the domain of this equation, the one I combined it. In other words, after I compressed it, I had an expression where minus square root of 10 works just fine because it becomes a positive number when you square it.
Mm-hmm.
So I guess what I'm trying to warn you about is with regards to domain restrictions, these are not equal.
Yeah.
And when you are checking domain, always go back to the original equation, not an intermediate one like this one. This is the intermediate equation. Minus square root of 10 does not fit there. So this problem would only have one answer. It would be the positive square root of 10.
And so a log, so if it was 0 and you're trying to...
Can't do it. Can't take the log of 0. That violates the domain. It has to be a positive number. It's worse than this function. This function can be 0. X can be 0. So the only restriction here is x has to be greater than or equal to 0. But when I say y equal log of x, x has to be greater than 0. Cannot even be equal to it.
Okay. All right. Guess we're going to the next one. The next one is just kind of out of geometric sequences.
Okay.
And it's, so the third number in the sequence is 180. And the sixth is 38,880.
And it's geometric?
Yep.
So the nth term, what's the general format for the nth term?
And, sorry, trying to remember.
It's the first term
times the rate, or the ratio, and then n minus 1 again.
Okay. So the fact that they've given us 3 terms allows us to generate 2 equations with 2 unknowns. The first term, a sub 3, we know that's equal to 180. It's equal to a sub 1. We still don't know the common ratio, but we know that it's 3 terms, so that's equal to that. So there's my first equation. 2 variables, a sub 1 and r, we don't know yet. Second equation, a sub 6 equals 38,880. Well, that's also equal to a sub 1 times r to the 5th, based on this equation. So now I have 2 equations and 2 unknowns, and I can solve. Anytime you give me 2 equations and 2 unknowns, I can solve it. I can solve it by substitution, or I can solve it by, the easiest way is to solve it by substitution. In other words, solve this one for r. So r equals the square root of 180 divided by a sub 1. Substitute that for r there. So I have 38,880 equals A1, this to the fifth. So it would be the square root of 180 over A1 raised to the fifth power. Now I have one equation, one unknown, A sub 1. I can solve for A sub 1, which tells me what my first term of the sequence is. And once I've solved for A sub 1, I can plug it into this and solve for R, which will give me both the common ratio and A sub 1. And then I'll have the specific formula. In other words, what they want is something that says A sub n equals some number, A sub 1, times some common ratio to the n minus 1 power. So your answer is going to look something like that. It's just not going to have nice round numbers like this.
All right.
But that's basically the way to solve. Whenever they give you two A sub n's, you're going to plug them both into the general formula to come up with two equations with two unknowns. And you can always solve two equations with two unknowns.
All right. Okay, yeah, I think I get that.
That's one of the harder kind of questions on geometric sequences. Most of them won't be that hard. Most of them will be, in other words, most of your questions on geometric sequences are going to start out like this. And they're going to say, what is the, and they'll give you a geometric sequence. Let me put a geometric sequence up here. There's a geometric sequence. So the nth term is going to be equal to what?
2 times 3 and then n minus 1. That has 1.
Exactly. So that would be the explicit equation for the nth term. There's also the recursive. Have you talked about that at all?
Yeah, recursive is an.
Recursive, yeah, recursive is always defining A sub n as a function of the previous term. Well, we know what it is. It's the previous term times the common ratio.
Yeah.
So that would be the recursive definition of this explicit definition.
Yeah.
Okay.
All right, and the next one is it's another geometric series sequencing, and it is it says, okay, so sorry, I don't know how to word this. So a number in the sequence is equal to 5,461. So S sub n equals 5,461. And then the common ratio is 4. And
Okay.
then the
S sub n means the sum.
yeah.
In other words, the sum of the first n terms. Well, we have a formula for that. What's the formula for the sum of the first n terms?
I don't know.
Now we know R. We know this. We don't know A sub 1, and we don't know N.
A sub 1 is 1.
Ah, okay.
Sorry.
A sub 1 is 1. So we can substitute that. And for this, we're going to substitute 5461. For R, we're going to substitute 4. Now we have an equation with one variable only. Now, it's not the easiest thing to solve for when your variable is in the exponent, so let's talk about that. How do I solve that?
Now you multiply each side by -3.
What next?
Subtract each side by 1. And then you have the log of...
Well, first divide both sides by -1.
Yeah.
Now, to solve this equation, because your variable is in the exponent, you take the natural log of both sides. Now what?
And then you just divide by 4.
Well, no, the reason we took the natural log of both sides is so that we can now take the variable and get it down on the equation line. In other words, we want to get it to a method where we can solve it algebraically. Well, this expression here is equal to n natural log of 4. And I'm trying to solve for n. So n is going to be the natural log of that number divided by the natural log of 4. And that solves our problem. In other words, the question was, what was the number of terms, right? In other words, since they gave you the sum, the only thing we didn't know was what is n. So the question must have been, what is n? If the sum is equal to 5461, and the common ratio is 4, and the first term is 1, how many terms are in this sequence? Well, that's the answer.
All right.
Unfortunately, Garrett, I have a 4 o'clock online also.
All right.
Today I had them stacked up back to back all afternoon. So I'm going to have to run. Hopefully that will have answered your most pressing questions.
Yeah, it did.
Good.
All right.
I will talk to you next time.
All right. Sweet. Thank you.
All right. Bye-bye.
Bye.